Okay, so thank you for joining me. In this video, I'm going to demystify the concept of dynamic programming. If you go into Google, you'll find this definition that I have over here on my screen. It says dynamic programming is mainly an optimization of a plain recursion. For example, it gives an example. If we write simple recursive solution for Fibonacci numbers, we get exponential time complexity. And if we optimize it by storing solutions of subproblems, time complexity reduces to linear. Okay, so there are a number of concepts that are mentioned in this definition that I want to, to sort of explain to you guys so that you can understand. Okay, before I go any further, I want to make a function that generates Fibonacci numbers. Okay, so over down here, I'm going to define a function. This function, you can find it on python.org. It's already there. So I'm going to call it fib. And if I pass n as a number, n is going to be a number. So n is going to be the ceiling. So it will generate Fibonacci numbers that are below that number. Okay, so over here, A and B, we initialize two variables, A and B. We assign them values of 0 and 1. We can assign them values of 1 and 1. And then we use a while loop. While A is less than the n, while A will be less than the number that we pass in, we want to print A and then end like this, equals to quotation marks. All right, this ensures that when we are printing the numbers, they're going to be printed from left to right. Not over here, we're going to do what we call variable swap, B, A plus B. This is what we call variable swap. Then down here, we will just print a blank line. All right, so if I'm to run this code, but I need to call the function fib, let's say fib of 100. So it's going to generate Fibonacci sequence numbers that are below 100. If I'm to run this, you will see down here, okay, it goes from 0, 1, because we started from 0 and 1. So we need to start somewhere. We need to have a place where we start. So we started from 0 and 1. And so the next one is going to be an addition of the previous two numbers. 0 and 1 is going to give us 1. The next number is going to be 2. It's going to be an addition of the previous two numbers. And so this sequence goes on and on and on. So Fibonacci sequence is about adding the previous two numbers to give you the next number. So as you can see from here, 55 plus 89 will give us the next Fibonacci number. And the same thing goes on and on and on. Okay, so if I'm to put 1,000 in the Fibonacci sequence, I want to generate numbers that are below 1,000. Control B, you realize that 55 plus 89 is 144. 144 plus 233 is going to give us 377. 233 plus 377 is going to give us 610, and then so forth and so forth and so forth. So this is the Fibonacci sequence. Okay, and then our problem now, let's say we are given a problem statement which says that we need to find the nth item on the Fibonacci sequence. So let's say we need to find the 10th item on the Fibonacci sequence. So the way it goes is 0 is just 0, 1 is 1, another 1 is 2, 3, 4, 5, 6, 7, 8, 9, 10. So 55 is on number 10. So we need to make to make a function that will find the nth item of the Fibonacci sequence. All right, so that's where we're going to apply our dynamism, our dynamic programming. And so we're going to define another function, which is going to be fib position. Fib position, the position of elements. We're going to pass in n again. And then this time, if n is less than or equal to 2, we're going to return 1. As you guys can see, 1 and 2, they are 1, so we need to return 1. This is the base case. Else, we want to do a recursion. Okay, now we're going to apply this recursion, the plain recursion. So we need to write recursive solution. So the way we do it is we return. Let me show this so that you guys can see. Now, recursion is a function that calls itself, right? So we need to call this function one more time. Fib pause n minus 1, since that's how we get the Fibonacci, and then fib pose n minus 2. Okay, so it's n minus 1, n minus 2. That's how we get this one, right? Let's try and run this function. Fib pose, we want to print it out since it's returning values, so it cannot print anything. So we need to use the print function to see what is on a particular position. Fib pose, let's say 10. We have it. Fib position 10 is going to be 55. So 1, 2, 3, 4, 5, 6, 8, 9, 10. You guys are thinking about the 0. The 0 is just position 0. Okay, you need to keep that in mind. 0 is just position 0. So let's say the 6th item, so it's going to be represented by a graph. Okay, so this is 6th item of the Fibonacci sequence. So what happens behind the scene is recursion minus 1 and minus 2. Okay, so 6 minus 1 is going to be 5, 6 minus 2 is going to be 4. The same happens on the other node. 5 minus 1 is going to be 4, 5 minus 2 is going to be 3. Alright, the same thing happens here. 4 minus 1 is going to be 3, 4 minus 2 is going to be 2. Alright, as you note, 2 is our base case, okay? 2 is our base case, so we no longer need to go down. And so we still need to go down here. 3 minus 1 is going to be 2, and 3 minus 2 is going to be 1. So now we have the base case. Over here, 3, we have a 2 and a 1. We hit our base case. We're done. On this side, 4 is going to be 3, and over here is going to be 2. This is a base case. Alright, and then here, it's going to be a 2 and a 1, base case. Now we want to calculate how this is calculating. So I'm going to use a different color. Okay, so we want to find the 6th element on the Fibonacci sequence. So this is what happens. These two base cases, what do they give us? They return 1, right? So 1 here and 1 here. So what happens when you add 1 plus 1? You get a 2. So what is the 3rd element on the Fibonacci sequence? You realize it's a 2. All right, and then the same thing over here, we have a base case, so 1. So we combine these two. 2 plus 1 is 3. So the 4th element on the Fibonacci sequence is going to be 3. The same thing happens. We have solved this side. We no longer need to go down on this branch here. We just need to replace this with a 2. It's the same thing. If we add 1 plus 1, we get a 2, right? So if we add these two, 3 plus 2, we're going to get a 5. And that's the 5th element of the Fibonacci sequence is a 5. All right, if we come to this side, since we already know that, you know, the 4th element is a 3, so when we come to this side, do we still need to go down and calculate? No, because we already have it over here, so we can just replace this with a 3. Because even if I'm to calculate, it's going to give me a 3. So we say 1, 1 here is going to give us a 2 up here, and then this is a 1, 2 plus 1 is going to give us a 3. So that's what happens. And so 5 and 3, 5 plus 3 is going to give us an 8. So 8 is the 6th element on the Fibonacci sequence. So this is what happened behind the scenes, okay? This is what happened behind the scenes. But I want you to take note, okay? The computer doesn't calculate all this at once. So it goes from left to right. It calculates and it, you know, it goes and then it calculates and then comes here and calculates and then comes here and calculates and then it goes to this side, comes here and calculates and comes here and calculates and then it goes to that side. I want to come to this concept of exponential time complexity. All right, so this happens in this function. Okay, this happens in this function. This function, it gives us exponential time. Okay, if we were to run this function, what we're getting is exponential time. All right, I'll prove that to you. So the first thing I want to do is explain what is exponential time. Okay, this is what we call the big O notation. is the number of operations that is required to accomplish a certain task. That's what we call the big O notation. So we pit time against the input size. That's what we do. So here we have an input size that is growing larger, and then we also have the time. So as you can see, if we have an exponential time, it simply means with an increase in input size, the time is going to increase exponentially. Okay, it's going to be on steroids. You understand? Like it's just going to rise like it's on steroids, like it's going boom up like that. So that's what happens when we use this function. So I'll prove it to you. So let's say I have 2 elements. So it's going to be 2 to the power of 2, because I have the n is the size of input, right? So I have 2 inputs. So 2 to the power of 2 is going to be 4, right? So let's say I add just 1, it becomes 2 to the power of 3. What's going to happen? What is 2 to the power of 3? It means it's going to be 8. So look at what has happened. This has been doubled. It has doubled the number of operations. So let's say I add in another element, 4. What is 2 to the power of 4? That is 16, right? And so you can see the pattern. It's 4, 8, 16. So each time you increase the size of your input by just 1 element, it's doubling the number of operations that you need to do. So that's thereby, making our time to rise exponentially. For now, it's working fairly fine. Let's increase it to 25. Let's say we put in 25 here, Control S, Control B. Okay, the time has increased a bit. As you can see, it's now 0.5. Let's increase it to 30, Control S, Control B. And now you can see it's now taking a bit longer. All right, 1.7. Let's increase it to 35 and see what happens. Control S, Control B. And now we have to wait. So look at this. Now we have to wait for 12 seconds to process this, the 35th. So as you can see, guys, time is increasing exponentially. If I'm to go to 40, we have to wait. Let's say 40 here. Control B, now we have to wait. You understand what I'm saying? So this is what's happening with this function, because it's recursive. It's working on 2 parts, this and this, this and this. It has to subtract 1 and subtract 2, subtract 1 and subtract 2, subtract 1 and subtract 2. So it's doing this recursively. So this is what happened. All right, so as you guys can see, it's taking the whole day. Okay, it's taking the whole day to do a simple task. We have it, as you guys can see, 132 seconds. That's a long time. We have waited for a long time. So we want to optimize this. So how are we going to optimize this? So this is what where we need dynamic programming. We need to apply the concept of dynamic programming. So the concept of dynamic programming, it stipulates that on one end we need to use recursion, of which we are doing so. But why are we not getting the optimum time? Since we are, using this recursive operation, there is also another element that we need to add in if we are to make it a dynamic, solution. So we need to store solutions of sub problems. Okay, we have already divided our problems into sub problems, but the solutions, we're not storing them anywhere. So we need to find a way to store them in some kind of a container. In Python, we're going to use what we call a dictionary as our container. Okay, so up here, we need to add a cache, which is going to be an empty dictionary. Okay, this is how we create an empty dictionary. Use curly brackets. All right, and then over here, we're going to add another base case scenario. If n in cache, what do we need to return? We need to return the cache n. So this is how we access the keys of the dictionary. So how information is going to be stored in here is going to be stored as key and value pairs. You guys, if you are familiar with dictionaries, it stores information as key and value pairs. So, and then here we need to cache n is going to be now we assign this as a variable to this, and then we return this down here, return cache N, just like that, and then cache, and then another cache, just like that. Okay, let's do it. 40, Control S, Control B. Look at how fast it took. Boom, instantly I got my results back. So that's what we call dynamic programming. Dynamic programming is just the concept of using a recursive solution, and then you have to create what we call a container to store the subproblems, and then you can easily access them here. You no longer have to repeat yourself over and over again. So that's the concept of dynamic programming. So the concept of dynamic programming is when you have answers for one side, you store them in a dictionary. So this is our dictionary. We store in our dictionary. So we know the third element is 2. This is how it stores it. All right. So the key and the value. The key is 3 and the value is 2. And then over here, the fourth element is going to be, so it goes like fourth element is 3. This is how it stores in the dictionary, okay? In our cache, okay? So, and then the same thing, the fifth is going to be 5. All right, so when it comes to the other side to calculate, it no longer needs to go down here. It just looks up in our cache, right? It looks up in our cache to check for these, keys. So this concept of keeping data or solutions in a container is what we call memoization. So up here, what's happening is what we call memoization. Okay, this is not memorization. You need to understand this is memoization. So that's a big concept. Okay, so we've actually used memoization to store our data, and then we can easily access the data when we want to use it. Okay, so that's where this word comes from. It's called memoization. This is the technique. All right, it's actually a good way to solve problems because it helps to cut the time that we have to use. Now this time is more linear here. The time is now linear. So linear time, for those who do not know, linear time is almost like this. It's the increase in time is in proportion with the amount of input that you pass into your function. So let's say we pass in 500 here. Control S, Control B, as you guys can see, it's still quite fast, really fast. But you cannot go beyond 1,000, I'm sure. Let me see, Control S, Control B. If you go beyond 1,000, you have this error. It's down here. It says recursion error. Maximum recursion depth exceeded in comparison. So I'll show you how to solve this. It's simple. What you simply have to do is you import the sys library, and then dot set recursion limit. All right, we want to set it to 10 to the power of 6 up here. I think it's the maximum right now. The default maximum is 10 to the power 4. So if I'm to save this and run this, boom, as you guys can see, I didn't have an error. So now it can calculate the Fibonacci sequence. So this is the 1,000th item. This number, this is this long. Okay, that's how long it is. It's this long. So if I'm to copy this, let me copy this and pass it here. Let me pass it here, Control V, and paste it here, and then Control S, Control B. You see what happens. You see these numbers that are appearing here. They're actually, that's a long. These are long numbers. You see, these are long numbers. Actually, we actually calculated the Fibonacci of this number here. So it goes here from 0, 1, 2, 3, and then goes 13, 21, and then it's going down to these quite quite long digits, as you guys can see. All right, so I want to thank you. I hope to see you in our next video. I'm out.